Proof by induction is a type of proof that works particularly well for certain theorems. I will explain it with an example. I want to prove that for every natural number n greater than or equal to 4, n factorial is greater than 2 to the n. If I only wanted to prove this for one value of n, for example for n equals 4, it could be very easy, just do the calculation and check it. But I have infinitely many values, so I cannot do it one by one. If I had a way to prove it for all values of n at once, I could do that. It would probably be the fastest. But I can't think of how to do that in this case. So instead, I'm going to try to write a proof by induction. I'm going to call the inequality, the thing I want to prove, Sn. This is just so I can refer to it easily. And in general, proof by induction is well suited for certain theorems that depend on a natural number, like this one. Here is the structure of a proof by induction. It has two steps. The first one is called the base case. I need to prove Sn for the smallest value of n, in this case 4. So I just need to prove S4. The second step is the induction step. I need to prove that for every n greater than or equal than 4, Sn implies Sn plus 1. So that means I'm going to be proving that S4 implies S5, S5 implies S6, S6 implies S7, and so on. And I don't need to do anything else. So I need to prove the statement for one value of n equals 4, and then I need to prove a bunch of implications. To be clear, in the induction step, I am not proving Sn, and I am not proving Sn plus 1. I am only proving that one statement, Sn, implies another statement, Sn plus 1. So in this case, I will be proving that one inequality implies another inequality. By itself, the induction step doesn't tell me whether any of the statements is true. If I only prove the induction step, it could still be possible for all the Sn's to be false. However, when I prove both the base case and the induction step, what can I conclude? Well, because I've proven the base case, I know S4 is true. And then, because I've proven the induction step, I know that S4 implies S5, so S5 is also true. I know S5 implies S6, so I know S6 is also true. I know S6 implies S7, so I know S7 is also true, and so on, and I will have proven the statement for all values of n, as I wanted. To summarize once more, I prove the statement for one value of n, that's it, and then I prove a bunch of implications, and the two things together are enough to conclude the statement is true for all values of n. Enough introduction, let's write down the proof. I'm going to write a proof by induction, but my reader doesn't know it, and my reader cannot read my mind, so I should mention that explicitly. First is the base case. In this case, what I need to do is prove the inequality when n equals 4. Well, that should be easy. Let's just do the calculation. 4 factorial is 24, and 2 to the 4 is 16. Done. That works. Next is the induction step. This is the more interesting one. What I need to do is for every n, prove that Sn implies Sn plus 1. So this should be for every n greater or equal than 4. So the first thing I need to do is fix a value of n, otherwise nothing will make sense, and it must be arbitrary. So I write let n be greater or equal than 4, which means I am fixing an arbitrary value of n greater or equal than 4. And then I need to prove an implication. I need to assume the inequality with n, and I need to prove the same inequality when I put n plus 1 instead of n. I assume that n factorial is greater than 2n, and I want to show that n plus 1 factorial is greater than 2 to the n plus 1. Now, how do I prove this inequality when the only thing I'm allowed to use is this other inequality? I know how to relate n plus 1 factorial with n factorial, because n plus 1 factorial is n plus 1 times n factorial. And I also know how to relate 2 to the n plus 1 with 2 to the n, because 2 to the n plus 1 is 2 times 2 to the n. I am trying to prove that this is greater than that. Well, I know that n factorial is greater than 2 to the n, so if I multiply this inequality by n plus 1, I can conclude that n plus 1 times n factorial is greater than n plus 1 times 2 to the n. And here in this step is where I have used my assumption. The inequality I'm assuming is true for n. This is called the induction hypothesis. And it's good to indicate in a proof by induction when we use the induction hypothesis. So now, can I also conclude that this is greater than this? Well, yes, because I have 2 to the n in both cases, and n plus 1 is definitely greater than 2, because since n is greater or equal than 4, then n plus 1 is greater than 2. And that's it, because now I have managed to prove that n plus 1 factorial is greater than 2 to the n plus 1, which is exactly what I wanted to show. And in order to prove that, I had to use that n factorial was greater than 2 to the n. So this completes the proof. To conclude, I want to address a common misunderstanding of what a proof by induction is. The induction step does not consist of proving the statement for n plus 1. It consists of proving that the statement for n implies the statement for n plus 1. It's an implication. So going back to how I set it up here, I've only proven the statement for one value, for 4. I have not proven it for n, I have not proven it for n plus 1. I have just proven it for 4, and then I have proven a bunch of implications. That if the statement is true for n, then the statement is true for n plus 1.